on this computer. So we're now recording. Okay. So statistical mechanics is based on probability, and basically this lecture is just going to be a review on probability theory. I'm going to focus for the most part on discrete probabilities because they're much easier to see how they work. And I'll have a few continuous cases at the end when I do about Bayesian learning. But almost all of it will be simply, as I said, addition, multiplication, division, those kinds of things. Oops. All right. I'm not going to go through the abstract because we've seen it several times. This is the material that I'm going to be talking about. And so we're going to focus, as I said, primarily on probability. And this is very important for statistical physics. And we're going to start with some simple ideas and progressively move on to more complicated ideas. And hopefully everything will, if you get any problems, please stop me and ask questions. That's the primary thing. One of the things
Bob,
that,
before
yeah?
you get started, Bob, could you get rid of the bookmarks part? Your display is only showing a small part of the actual presentation.
I don't understand. What is the,
like if you look at your screen, you're on the left-hand side, it says bookmarks.
it doesn't on my screen.
Oh,
It does on mine.
Yeah,
Huh.
It says abstract introduction, God's probabilities versus
Yeah.
observed probabilities.
Oh, you mean this stuff up here? This is just part of the presentation.
well, but it's taking up a lot of space. If you click on the X next to the bookmarks, then it will make the actual presentation bigger.
You're not sharing the screen you're seeing.
Yeah, we're seeing a different screen. Move your mouse. I think we're seeing a frozen screen from something that you screenshot or something.
It's the beginning, Buster.
I'm clicking it and sharing it again. Is this any better?
Better.
Yeah, there we go. There we go.
Okay, good. Let me now get the hell myself closed. There. All right. Okay. So one of the things that most people don't realize is that probability is empirical and observer dependent. And we'll talk about that a fair amount about halfway through the lecture. The second important idea is that the combination of systems, each state having a probability of occurrence, can be described in a couple of different ways. Collections of systems, possible combinations of states, can describe properties of the collection. This is going to be important next week. So I had hoped to get there by this time, but I didn't have enough time to get through the material for it. So people usually have various kinds of things for randomizing properties, and the one that most people think of immediately is coins for randomization. You get half, if it's a fairly evenly distributed coin, most of the time it'll come up half one side and half the other. There are lots of other types of machines that people use for approximately behaving random properties. So we have various kinds of symmetric uh, objects here that have 6 sides and 8 sides and 10 sides and 12 sides and 20 sides and 4 sides. And those are other ways of doing things for randomization. The mathematicians talk about it in terms of the Kolmogorov axioms. And although it is true and it does actually work, it's not very informative for non-mathematical readers. Let me just try to explain. The axiomatic approach was primarily pushed by Hilbert around the beginning of the 1900s. And in particular, he was very important. He was very interested in statistical mechanics. And he set up, you know, I forget how many problems that he had set up to understand in mathematics. The 6th one was the investigation on the foundations of geometry, and by the means of axioms. Basically, the idea was that, you know, Euclid had set these axioms up and all of geometry followed from it. So he wanted the same thing to be true in physics and all forms of mathematics. And one of the first things he wanted to understand was an axiomatic theory of probability and statistical mechanics. And while probability does have some extra ideas relative to the rest of mathematics, what he really wanted to know was, is there some new technical ingredient needed to be added to the rest of mathematics? Kolmogorov his achievement was that it didn't need anything new. Recently, measure theory had been developed to resolve the ideas that had in set theory, and they had found a axiomatic way of defining that every region in the plane has some area. And that was not that they couldn't do it with Riemann theory, but it was a different way of doing it. And someday maybe I'll tell you a little bit about measure theory. It's actually pretty straightforward, but we'll pass on that for the time being.
Are you talking about Lebesgue integration?
Yeah.
Okay.
Yeah. Anyway, he realized, Kolmogorov realized, that you could have one special model within probability, pick a uniform random point in a unit square, and that could be defined in terms of measure theory. So he had these 3 axioms. Probability of an event is a non-negative real number. It's a positive number, a real number, not a ratio, but some real number. And it has at least one of elementary events that occur in a sample space. So part of what he said was that everything that happens in the way of events, that collection of sets has a probability, and each event has a probability of its events. and the sum of all of them, somebody's, okay. All right, so there are consequences. One is monotonicity. If you have a set of events, a collection of events A, and another collection of events B, and A is a subset of B, then the probability of A is less than or equal to the probability of B. And the only way that equality happens is if the two sets are identical. So the other one is that the probability of the empty set that is having no events has probability 0. If you have the collection of all possible sets, and A is a collection of the events in, I'm sorry, the collection of all possible events is omega, and the collection of events are A, then the probability of the complement, if you remember from basic stat theory, if you have a collection of all possible events omega, the complement of A is everything that's not in A, but is in omega. And so the probability of everything is 1, and whatever the probability is for A, so the probability of the complement is 1 minus the probability of A. So there's also a numeric bound. Every collection of events in omega, somebody's got their sound going and it is making noise. Would you please all mute your sound? And then when you need to ask a question, just press the space bar and your voice will go back on. So if everybody would please mute their audio, I'd appreciate it. Okay, so every probability event or collection of events is between 0 and 1. Everything so far, I hope, is pretty straightforward. If there's any questions, please stop me immediately. Don't wait until later to ask. All right, there is a little bit more complex rule, the addition of probabilities, or the sum rule. On the bottom, I have two sets, A and B, and the union is the collection of all events that are in either A or B, and the intersection of A and B on the right is all of the sets that are in A and B. So all of that's, I assume, fairly straightforward. The probability of the union of A and B is the probability of A plus the probability of B minus the probability of A intersection B. And if you think about it, if you have the probability of all of A and you have the probability of all of B, you've twice counted the intersection because the intersection is in both of them. So the sum of A plus the sum of B has twice the probability of the intersection in it. So you have to subtract one of them off in order to make the probability of the union. Is that understood? Is that understood? I'm assuming by quiet. Remember, you can hold your space bar down and you'll be able to ask any questions.
I've got my 6%.
Well, this should be 100%. This is fairly, you've got all of the stuff here, you've got all of the stuff here. This is in there. This one has one total count of this. This one has a second amount of sets, the same set of events. So the probability of the union has twice the probability of the intersection. So subtracting 1 means that you have counted the right number of events. Is that clear, Art?
So
Yes.
is
Chris, you have a question?
is the union, is that the probability of one thing plus another, or?
It's a collection of all events. So this is a collection of events that happens in omega. This is another collection of events, but some of them are in both of them. So if you think about, say, rolling a dice, okay, you could have the events could be a 1, 2, 3, 4, 5, or 6. Okay, so if you took the even ones in here, and then you had another one which was all of them, this would actually be a complete subset. So I'd have to think a little more complicated in order to have it the way I have it done here. But if you added the probability of all things, you'd add the probability of all 6 events plus all the even events. So you'd have them copied, you'd have the probability added twice.
So you subtract the intersection.
So you subtract the
Okay.
the probability of the intersection off in order to avoid that double counting. Okay, great. Thank you. Okay, so let's consider an idealized coin, an infinitely thin, so that the edge is not stable and can't stand on it, and the only events are heads and tails. The collection of all possible events, omega, are heads and tails. And the power set is the empty set, the set of heads, the set of tails, and the set of heads and tails. Now, Kolmogorov's axiom says that the empty set has probability 0. How do we write the event neither head or tails? Anybody? The total events are heads and tails. So the complement rule that we said before is everything that's not in heads and tails. That's got to be the empty set. And therefore, the probability of the empty set or the complement of everything is 0. So I'm just trying to have people to think about the way in which the collections of events happen and how the set theory works with it. Okay, the probability of either heads or tails, that is the union of heads and tails, is the probability of heads plus the probability of tails minus the probability of the intersection. The intersection heads and tails do not intersect. It can't be heads and tails simultaneously. So the sum of everything is 1, and you take the empty set. So this is, again, just 1 minus 0. So the sum probability of heads is the probability, I'm sorry, the sum of the probability of heads and the probability of tails is 1. There's no way to assign a value of probability to heads and tails. That is, you can't have a heads and a tails event in the set. It's either heads or tails, but not heads and tails. All right, there are two types of probability theory. One is often called frequentist, and these are where God assigns a priori the probabilities of the events in omega, the set of all possible events. Frequentists believe that probabilities exist independent of everything that has ever been observed. A different type of probability is Bayesian or observer probability. And the observer assigns an uncertain value of the probability of each event and a priori based on his or her state of knowledge about the collection of events. So frequentists typically try to use some kind of symmetry argument to apply everything as being equally likely, such as a coin or a six-sided die. But in reality, it's almost impossible for any real kind of a event to have a pure symmetry. So as an example here, we'll have a non-symmetric approximation to a coin, a thumbtack. So obviously, this is not going to be, you can have two types. You can have pin down or you can have pin up. So it's just like a coin, but the odds or the chances, the probability of up and down for the point is not going to be symmetric. And there's no way that you can use the symmetry to understand this. Everybody's had thumbtacks around. Some have their experience will be different. Some people will have walked into a thumbtack and the point will have gone into their foot and they will really not like it. But they might think that pin up is much more likely than pin down. Other people might notice it always being in the carpet, so they'll assume that it's mostly pinned down. We know from the physics of a tack, if it has a really long pin, as the pin length goes to infinity, the probability of pin down is going to go to to 1, because it's unstable and it always falls over. So if the pin length goes to infinity, the pin down probability goes to 1. However, as the pin length goes to 0 at the other end here, it goes back to being a coin. So the pin up and pin down is going to be somewhere between 0 and 1, but you don't know whether it's less than a half, more than a half, unless you've had a lot of experience with thumbtacks and flipping them. Has anybody ever spent any time doing that?
So Bob, is this the buttered toast always falls on down? Is that the rule here?
Well, we'll talk a lot about this later, but it's a a typical way of understanding the Bayesian point of view that the probability is not something that you know a priori. You don't know, it doesn't observe, you have to actually do experiments in order to understand what the probability of the events are.
Yeah, I think as a first approach, you would have to take the vertical axis and ask at what angle the pin length would be, at which point it would fall down on its side versus riding up on its head. If you knew that angle, then you could figure out from that solid angle what the probability would be, assuming that that's the only consideration involved.
Well, I do it experimentally, and that's the way I've always done it. You can do a small calculation on the side, give a presentation, and send it out to us.
So you want to flip it a couple of million times?
Well, you'll find out later. I've only got the information on 90,000 flips, but there are some people who've only done a few. So, okay. So, does anybody? We're assuming that the cap is uniform density, that the size is about 3/4 of a centimeter squared, which is about 0.3 inches radius or diameter, I think. And the pin length is about 0.22 inches, 0.55 centimeters. Oh, I'm sorry. The first was the diameter, not the area. That was just the footnote. Okay.
Is the head flat? It's rounded in your picture, but it makes a difference.
Well, the ones that I have personally experienced with had flat tops, not rounded ones, but the pictures that I found had rounded ones, so that's the way I showed it.
Okay, but so we're talking about flat.
Yeah, the ones that I know about all have flat thumbtacks.
Is it hitting a solid surface?
Yeah, the experiments that I have seen done where people took a box of 5 dozen pins, and on a ordinary desk in a class, they would take them, throw them over, and then count how many were down and how many were up. So it was a hard surface that they were thrown on. If they slid off the side of the desk, the floor would also, of course, be hard, and they would just count the way they were when they picked them up off the floor as part of the counting that was going on. Okay, so
what if they landed on the pin vertically?
Well, they were a hard surface, so they wouldn't stay there.
So you mean quantum fluctuations would eventually cause them to keel over?
Well, no, I'm saying that they lifted them a foot, you know, a good 6 to 12 inches off of the surface and dropped them, and there was a lot of momentum. So if they came in point first, they would not stay there because it was a hard surface, not able to, not a rug where they might hold them or something like that. So Bayesian probability or observer probability, you model the data and quantify the uncertainty of the predictions. You incorporate whatever knowledge you happen to know, and I've already, you know, given the the result, I know much more information about pins than almost anybody else in the room, because I have knowledge about 90,000 flips, and most people might have, you know, a dozen or something like that.
You've been busy.
Pardon?
You've been busy.
Well, personally, I've only done 3,000, but I know of, I'll tell the story later about how I got to 90,000. Anyway, this incorporates your prior knowledge. It incorporates optimal predictions, and it allows for decision theoretic reasoning, not just probabilistic reasoning. So we're going to run an experiment. I have a thumbtack, I flip it, the probability shows that 4 of them came up and 3 of them came down. So we have 0.57 as an estimate for the probability of pin up. But so what? We'll talk about the so what fairly on down, but first I need to do a little refresher in basic probability. First thing is random variables. Random variables are some aspect about the world about which we have some uncertainty. So R might be, is it raining? And of course that means where, because somewhere around the world it's raining. But we're talking about in a particular location. And D might be, how long does it take to drive to work? Well, for me, that's 0 because I don't work. And for other people, that might be a long, long drive. There were times when I was working that I'd have to get on an airplane and fly across the world. So it was a long drive to get to work. The other question, L, is where am I? So typically the notation is such that random variables are used with capital letters. So I've called them R, D, and L. All random variables have domains. That is, they have a set of possible answers. So is it raining here in Thousand Palms in the desert? And the 2 possible answers, the domain, are true or false. And sometimes this is written as plus R and not R, as there in some notations. If you ever run across them, you'll see what it means. The distance is something between 0, which I said is my result since I'm not working, and it could be as long as infinity if you never get there. No matter, you know, you could be going to the edge of a, you could be watching somebody driving off to the edge of a black hole, and that would take an infinite amount of time from your point of view far away. And so it would take an infinite amount of time for them to drive there. The location has to have some kind of coordinate system. So I said could be 0, 0, could be 0, 1, there could be some 0.75, 0.7, 0.7, whole bunch of things. So random variables have outcomes, and the set of possible outcomes is a collection that's the domain. Probability distributions. We're going to talk, as I said, mostly about discrete random variables. So I'm going to talk about a discrete distribution is basically a table of probabilities of values. So here we have the temperature, warm and cold, and so the domain is warm and cold. The variable is called uppercase T, and the probabilities here are 0.5 and 0.5. So the temperature being warm or cold is the same as a flip of a coin, a fair coin. We could be talking about the weather. We could have the domain of the weather W be sun, rain, fog, a meteor hitting the earth. And because I've only done things to 1 degree, 1 digit of accuracy, the sun will be 60%, the rain will be 10%, and the fog 60%, 10%, and 30%, and 0 for the meteor hitting. That's not completely accurate, but for the degree of accuracy I have there, that's close enough. So a probability is a single number. So the probability that the weather is rain is 0.1, or sometimes just written as P of rain equals 0.1. And we must have that all of the probabilities are greater than or equal to 0 for every event in the domain. So this is all of the probabilities are greater than or equal to 0 for all. That's what this symbol is. And X is in the domain. So for every event in the domain omega, every probability has to be greater than or equal to 0. And the sum over all events in omega, the sum of those probabilities has to be equal to 1. Those are the basic properties that we've talked about before from the Kolmogorov axioms. I'm going to talk about a slightly different kind of structure called a joint distribution. So a joint distribution over a set of random variables, and there could be n of them. N is some integer, and it specifies a real number for each assignment. So you have there's a domain for x1, there's a domain for x2, there's a domain for x3, etc., all the way to xn. And for every possible event in x1 with an event in x2 and an event in x3, etc., up to an event in xn. And so every one of those possible combinations has a particular probability associated with it. That's what this notation says. Every possible combination of events has a probability associated with it. So the size of the n random variables, this is called the Cartesian sum. So you can take all of the domains and take all possible combinations. That's what this says. And each one has a domain of size d1, d sub I events in each of them. So the probability of each one is greater than 0, and the sum over all possible events in the possible total combination of domains of the probabilities is still equal to 1. This is a basic property of all probability distributions. So for the smallest one that we have here, we have temperature, hot and cold, and we had weather of rain and sun. So we write it out in detail. So T has a domain of hot and cold. W has a domain of sun and rain. So all possible, there's 2 and 2, so the total number of possible outcomes is 4. So that's what this would tell you, that there are 4 possible outcomes. And those possible outcomes are hot and sun, hot and rain, cold and sun, cold and rain. And for every one of those possible combinations, there's a probability associated with it. So I've got 40% chance of hot and sun, 10% chance of hot and rain, 20% chance of cold and sun, and 30% chance of cold and rain. And if you notice, 0.4 plus 0.3 is 0.7, plus 2 is 0.9, plus 0.1 is 1. So this is a probability distribution. You've got all possible combinations, and you've got the appropriate probabilities. That's a joint distribution. There are ways to sum over those probabilities, and they will give you what are called marginal distributions. These are subtables, so you sum over or marginalize the joint probability. So if we're going to find the probability of the temperature, hot and cold, we have to sum over all the probabilities that have a weather for a particular temperature. So if you take hot and hot, you sum and rain, it's 0.4 plus 0.1, hot gives you 0.5. For cold and sun and cold and rain, it's 0.2 plus 0.3. That also gives you 0.5. So you get hot 0.5 and cold 0.5. The other way that you can marginalize is by summing over the weather as opposed to the temperature. So here, the probabilities, the marginal probabilities over the weather, you sum over all possible temperatures in the domain of the temperatures. So here, if we want to do sun and rain, sun for hot is 0.4, sun for cold is 0.2, 0.2 plus 0.4 gives you 0.6. So sun gives you 0.6. And you can either go through and do the sum, or you know that the total has to be 1, so that means the rain has to be 0.4. Is this all, is there anything anybody needs a question about, has a question about? Okay. So a little more complex are called conditional probabilities. So there's a relationship between a joint and conditional probabilities. In fact, the definition is the probability of A given that B occurred is the probability of A and B divided by the probability of B. So it's again the same sets that we're talking about. We have the set of A and the set of B. and the probability of A and B, which we saw was the probability of A plus the probability of B minus the probability of the intersection a little bit before. And we have the probability of B, that's this whole, the probability of that whole area. So what's the probability that the weather will be rain given that the temperature is cold? Art, you wanna do this one?
I really don't.
Come on.
Now,
Point four.
We're asking for what's the probability that it's going to be rain given that the temperature is cold.
Oh, then it's 0.6.
Well,
0.3.
the probability of A and B, that is the probability of rain and cold, is 0.3. The probability of B, which is cold, is 0.2 plus 0.3, 0.5. So we had 0.3 divided by 0.3, or 3/5. And if I did that correct, it turns out to be 0.6.
0.6, right.
Right. Okay. So did everybody understand how this worked?
Yeah, so wait, so this isn't the probability of rain and cold. This is rain given that it's already cold.
Yes.
Okay.
So this is the probability of rain and cold. That's 0.3. Probability that the temperature will be cold is 0.5. The probability that it will be rain, given that you know it is actually going to be cold, is 0.6. All right. Conditional distributions. Conditional distributions are probability distributions over values, others fixed. So we have the conditional distributions, the probability of sun given that T is hot, and the probability of rain given that T is hot. Here, the probability that the weather is sun given that T is cold, and the probability that rain is cold is 0.6. So these are the conditional distributions. The joint distribution we had from the previous one. The joint, you just take the probability of B, multiply it by P of A given B, and you get P of AB. The joint distribution. So the joint distribution, you have to simply take the marginal distributions and take the conditional distributions, multiply them together, and they give you the joint distributions. This is known as the product rule. So if you want a probability of X given Y, it's probability of X and Y divided by the probability of Y. Or if you cross multiply, the probability of X and Y is the probability of X given Y times the probability of Y. So again, given our weather and the probability of whether it's wet or dry, given that it's sun or rain, you can multiply these by these and you get these results. So that's the product rule. A conditional probability and a conditional probability and a joint distribution are related to each other this way and obviously the same way. So you can work from one to the other or back and forth. Is that all clear? Great. The last thing, and the one that turns out to be very important, is Bayes' rule. So we can take a probability between two variables, x and y, and we can write them as the probability of x given y times the probability of y, or just the same result, you can do the probability of y given x times the probability of x. So these are two different ways to write the same product rule. And if you now divide them, you can get the probability of x given y is the probability of y given x times the probability of x divided by the probability of y. So this is, Thomas Bayes was I think he was in the 1700s. He was a clergyman, and this picture of him is actually not very accurate in the sense that this was the clergy robes that his father, who was also a clergyman, used to wear. And this shows him, although they were not common in the time when Thomas Bayes was, he would sometimes wear his father's robes. And this particular picture, which was taken from Wikipedia, has him in the non-traditional clergy rules for his time. They were for his father's time. But this is what he looked like. Anyway, he was the one who figured out this rule. And why do we care about it? Well, you can build one conditional from its reverse, and it's often conditional is tricky, while the other one is simple. And it's the foundation of many practical systems, such as automated speech recognition, machine translation. All of these things are based on this particular rule. So much of what we do in our mobile phones, where you can say a question and it will be translated into words that will be put into your into text on your mobile phone. It's all based on this rule. So it turns out to be very, very important. And of course, it's where the name for Bayesian probability comes from, because we use this rule to learn about events that are observed. So we're going to do a rule on, we're going to use Bayes' rule. I think everybody's probably heard of the Monty Hall show, Come On Down. On the game show, you're asked to choose between 3 doors, 1, 2, and 3. And you choose a door before knowing anything about what's in here, except that 2 of them have a goat and one of them has a car. And we're assuming that you would much rather have a car than a goat. That's true for me. I hope it's true for all of you. Anyway, for the problem, that's what we're trying to understand. So you know that one of them has a car, one of them has, and two of them have a goat. You have to choose one of the doors. So you choose one. By the rules, Monty always shows you one of the two that don't have a car. That is, they have a goat. So assuming here that you chose one, you know, the goat, assuming that there really was a car in one and you chose it, two would have a goat and three would have a goat. He shows three. He could have just as easily shown two. Doesn't change the results of anything. So the question he asks after he shows you that there's a goat, and remember, you don't know, it could be in here, it could be in this one. He asks whether you'd like to switch the choice from the one you had before or stick with the one that you originally chose. Would, let's see, Chaz, what do you think?
I'm trying to remember the answer to that thing that I heard about years ago, and I can't remember it.
Well, think about it. Tell me what you think would be the right answer.
I really don't know.
Okay. Bob Lukowski, what do you think?
I change because the reason is in the first place I had one chance out of three of winning, and in the second place I have one chance out of two of winning. So I'll change.
Okay, your numbers are a little wrong, but your answer is correct, and we'll show using Bayes' rule why that's true. Okay, without loss of generality, we'll assume we pick door one. Everything can be permuted and you get all the same results regardless of what one you picked and which one had the car, etc. We'll show that in a little bit later. Bayes' theorem is the formula for how to update the probability that the hypothesis is correct given evidence. That's what Bayes' theorem gives you. So in this case, I want to compute the probability that our initially picked door is the one behind the car, has the car behind the one I chose. And given we know that Monty has opened the door and shown a goat. So Monty has given us evidence that one of the choices we didn't pick was the wrong choice. So is this evidence useful? Okay, so I'll make my hypothesis that the door one has a car behind it. I don't know if that's true or not, but that's the hypothesis. The evidence is that Monty has revealed a door with a goat behind it. Then the probability can be restated as what is the probability of the hypothesis given the evidence? The conditional probability of H given E. So to compare this probability, I got to compute the probability of the remaining door. Since every door either has a car or a goat behind it. The alternate hypothesis, not a door. I'm sorry. Let's see. The hypothesis is door one has a car behind it. The not hypothesis is that door one has a goat behind it. So using Bayes' theorem, we have the probability of the hypothesis given the evidence is the probability of the evidence given the hypothesis times the probability of the hypothesis divided by the probability of the evidence. Okay, so these two parts are the same. Doing the expansions that we've done previously, the probability of the evidence is the probability of the evidence given the hypothesis times the probability of the hypothesis plus the probability of the evidence given not the hypothesis being true times the probability of not the hypothesis. Is this all pretty straightforward?
Yeah.
Okay. Would somebody tell me what the probability of the hypothesis is? Remember, you chose the 3 doors without knowing any information about, no evidence. There was no evidence at the time you made your hypothesis that door 1 had a car behind it. So what's the probability of the hypothesis? Kathleen?
I think you're muted, Nuggy.
All right, Chris?
Oh, I think it's 1/3.
Correct. That's right. Okay. So what's the probability of not the hypothesis? Art? Art, are you there? We know that the probability of the hypothesis plus the probability of not the hypothesis are the only two.
2/3.
Good. Yes, that's correct. 2/3. Good. All right. Now let's talk about the evidence given the hypothesis. Okay. So suppose that the hypothesis is true. What is the probability that Monty will reveal a door with a goat behind it? Jessica?
1/3.
No, it's
2/3.
it's actually 1, because he knows which ones have a goat behind it, and whatever one that has the car behind it, if you've chosen a goat, he'll choose the other goat, and if you've chosen a car, he'll choose one of the 2 goats. So
Okay.
it doesn't matter what hypothesis you've chosen. Now, how about the evidence for your hypothesis being not true? Let's see. I don't have my participants here.
0.
Pardon?
0.
No, it's 1, just as the other one is, because he knows which one has the car, which ones have the not car, and whether you chose a car or you didn't, he can always do one of the 2 that has no car in it and show it. It's independent of what you chose. I mean, so it doesn't matter for him which one is the hypothesis is true or not true. So both of them are one. Whoops. So the probability that the hypothesis is behind that door is 1/3, which Art, I think, said was, I think it was Art. Anyway, somebody did. And the probability that it not being behind the door is 2/3. The probability that the evidence Monty shows a door behind with a goat doesn't matter what your hypothesis is accurate or not. So it's 1 in that case, and it's 1 in that case. Okay. So now we do the calculations. We have the probability of the hypothesis given that the evidence was given. Now, the probability of the evidence given the hypothesis times the probability of the hypothesis. This one is 1. The same one there is 1. This one we've said is exactly also the same, so they're all 1s. The probability that you chose properly is 1/3, and that is the same 1/3. The not was 2/3, so we have 1/3 divided by 1/3 plus 2/3, which gives us back our original result of 1/3. So the probability that the car is behind door 1 is completely unchanged by the evidence. So the fact that he showed you one of the goats didn't change your probability of having originally chosen the car. However, you know that you have 1/3 chance of it being behind your door. You know, the one he showed you is not. So the probability that it's behind the one shown beside you, the one that he didn't show, is 2/3, because you have a chance of 1/3, and it's either in the two of them. So the sum of the two is 1. So the probability of the other door is 2/3. So switching is twice as likely to get you a car as staying. Is this at all surprised? Are people have?
Yeah, that's pretty
That's
crazy.
a total surprise to me.
It's complete surprise to me, and I don't think it makes sense.
Oh, it is perfectly true, and I'll show you another way of seeing why it's true.
So another way to think about this is assume there were 1,000 doors and you picked one. The chance of your picking the correct one is 1 in 1,000. Monty then eliminates 998 of them. You want to go with your chance of 1 in 1,000? Now you've got sort of one other opportunity to choose.
Does that make sense? Jack is
Yeah,
absolutely correct.
That helps, yes.
I don't think it helps. It doesn't. Once Monty eliminates one of the doors, it changes the game, and now you are looking at 2 different doors with a 1 in 2 chance.
No, that's
Getting
not
it
true.
right.
You only have a chance that you originally chose. Your probability is the probability when you did the choice. You didn't have the information. You choose 1 out of 3.
So what information do you now have?
You now know that the other door has twice the probability you do.
I still don't see it.
Well, try this one.
I mean, when you are doing this, okay.
Choose this one. Okay, you're asked to choose a door. You choose a door with a goat behind it. If you stick, you get a goat. If you change, you get a car, because the third possibility was eliminated. So there's only the last door that is there must have the car, right? Because you chose a goat behind it, right? So
Right.
if you stick, you get a goat. If you change, you get a car. Suppose you choose a different door with a goat behind it. If you stick, you get a goat. If you change, you get a car. Suppose you choose a door with a car behind it. You stick, you get a car. You change, you get a goat. So if you stick, you get a goat, you get a goat, you get a car. One chance out of 3. If you change, you get a car, you get a car, you get a goat. 2 chances out of 3. So much better chance of getting a car if you change. Did that make it clearer?
Well, that is clear. What happens if you chose the car originally?
Then you get a goat if you change.
Right. So how does that? Yeah. Okay. So are you?
We're
then
not talking absolutes here. We're talking probabilities.
probabilities, right?
So there's twice the chance of changing. If you change, you get a car, you get a car, you get a goat. Twice as likely to get a car than if you get a goat. If you stick, you get a goat, you get a goat, you get a car. So the odds are twice as large you'll get a goat if you stick.
Well, then are you saying that in this, and by the way, I looked it up, the name of the program was Let's Make a Deal. It wasn't door number 1. But are you saying then that all contestants should always switch?
Yep, absolutely. That should, if you ever stick, you get twice the chance of getting a goat than if you get a car.
Bob, many
Yeah.
years ago, I tried to teach this concept and had struggled with doing so, but I never used a graphic like this. This graphic is an excellent way of describing what happens. And then you can go back and go to the mathematics, but this is really well done. I appreciate it.
Okay.
Yeah, I was gonna say this. I've seen videos on this problem, but I never really got it. But this explanation really helps.
Okay. Well, I spent 40 years doing decision analysis, so this is the kind of stuff I did for people as a consultant all the time. That's why I chose it. Anyway.
I just want to ask one other thing. If this is so,
It's not,
or
if
I mean, it is so. Okay,
it is
this
so.
is so. Okay, this is so. Why didn't why wasn't this revealed at the time the program was active and common knowledge, and every contestant switched, and it totally defeated the game, or the probability?
It was
Well,
revealed.
because people don't understand about Bayes' rule, don't understand about decision analysis, and they also are not very informed. So in point of fact, Savant, Marilyn Savant, I think her name was, or something like, whatever, the one who had a parade magazine article about this. I mean, even statisticians and all kinds of people said she was wrong because she came with this result. And people just have made this mistake over and over and over again, and they don't believe it. So it was in the papers, and people still ignored it.
Okay.
So that people just, you know, one of the things that psychologists have found is that probabilities, understanding, I mean, people's understanding of probability, their intuitive understanding of it is horrendous. It is absolutely terrible. Unless you actually calculate everything out, almost always you'll get the answers wrong if you try to guess what the answer is. So people just, their experience, you know, in evolution was very good for doing things like mechanics. We can see a ball hit and run to the right place and pick it up and, you know, get it before it comes down very well. That, all of that stuff we've done very well evolutionarily, but we haven't had to deal with probabilities in evolution, and our ability psychologically to deal with probability is terrible, absolutely terrible. And let's see, Tversky and Kahneman have done a wonderful, well, Tversky died before Kahneman did the book, but the book was based on both their work. And it's called, I think something, you know, thinking fast versus thinking slow,
It's
or
called
something
Thinking
like,
Fast, Thinking Slow.
yeah. And that's an excellent, excellent book that explains much of the problems that people have with this. And Kahneman and Tversky were actually colleagues of mine at Stanford Research when they were starting into this area. So I learned a lot of it from them early on.
So one of the things that I think might be relevant here is ask yourself how many of these decisions about COVID-19 policy mirror this, that people don't understand how to assimilate the evidence in a way that actually allows them to sort of choose door two, even after they chose door one. It really is startling.
Yeah, you're absolutely right. The people, you know, are just completely ignoring all of the, I mean, there's this whole group of people who are out there assuming that vaccines are, you know, made up to kill people or something, and they refuse to vaccinate their kids. I mean, it is just completely without any understanding of how probabilities work and how vaccines work and how disease works. So you're absolutely right, Jack. Okay.
And during my talk in 3 weeks, I can get back to that subject.
Okay, great. Anyway, so how about our thumbtacks again? All right. So the Bernoulli distribution is that whatever the probability of up is some number theta, the probability of down is 1 minus theta. We assume that all flips are IID, that is independent. There's no autocorrelation. No matter how many numbers of flips you've done, the next one will have the same probability theta and 1 minus theta. And they're all exactly distributed by these probabilities theta and 1 minus theta. And because of the independence, the only thing that matters is the number of flips up versus the number of flips down. So for any collection of flips, the total probability, given that there is some value theta, would be theta to the number of flips up times 1 minus theta times the number of flips down. That all fairly straightforward?
Yes.
Okay. Why have I asserted that probability is observer dependent? Well, the probability parameter may have uncertainty. And in fact, most people probably don't know much about the probability of thumbtacks being pin up. And I'll tell you a little bit about my experience. I first ran into the tack flips in 1977 when I was auditing a decision analysis course in the operations research department at Stanford. The teacher, Ron Howard, pulled out a cabinet of boxes of thumbtacks. Each one had 5 dozen in a small box. He handed them out to each student, asked each one to dump them on the desk and count the number of up flips. Then he counted the numbers from each student and placed them on a spreadsheet. Ron had been doing this in classes starting in 1963 when he taught at MIT. Howard Ray. Jessica, could you mute your audio, please?
God damn it!
Jessica, mute your audio. Okay. So Ron had started doing this in 1963 when he taught at MIT. Another operations research person, Howard Rafa, had started doing the same thing at Harvard at the same time. There were 2 other people at MIT in the operations research department, Myron Tribus and Dick Smallwood, who were also doing this experiment while they were at MIT. And they all of them collected the information together. About 1970, Ron went to Stanford from MIT. I don't know whether it was Ron or Howard or Myron Tribus or Dick Smallwood who started it all about this, but they collected and shared all of the results. By the time I had seen this in 1977, there were over 60,000 flips on record. And I followed up and I personally had done 3,000 tack flips since then. And by the time I taught in the operations research department in Stanford in 1992, the number was over 85,000. So my experience is probably a little bit more than most of you. So how do I use my experience? Well, suppose I don't have any knowledge about what the probability value theta is. It could be just almost anything between 0 and 1. I would call this my description of my prior experience. That is, I have virtually no information. So this is a prior probability distribution. So, you know, there's 0 chance that it is 0, and there's 0 chance that it is 1, but it's almost always anything between 0 and 1. So initially we had 7 flips, and there were 4, and therefore 7 minus 4, 3 is the number down. Using Bayesian learning, we go back and we do the probability of the data given theta is this, and we use Bayes' rule. We have the probability of theta given the data, which is the probability of the data given theta, times the probability of theta and the probability of the data. Now, if you notice, the probability of the data is just a normalization constant. So you can actually ignore it in doing the calculations. And then when you're all done, you just sum everything up and you get the result from using this times this, and that's got to be what this number is, since everything always has to equal to 1. So you simply integrate over this to get the area under the curve, and that gives you the number to divide by. So my prior was the one that I just shown was theta to the 11 divided by 10 times 1 minus theta divided to the power 11 divided by 10. That's what this one looks like. And we said that there were 4 up and 3 down. So theta to the 4th minus 1 minus theta to the 3rd. And ignoring the normalization constant, that means that you get theta to the 51 divided by 10 divided by 1 minus theta to the 41 divided by 10 power. So if you integrate that number between 0 and 1, it's got an actual number in terms of gamma functions, which you don't need to know about. Consider that to be abstract art. But the number is 0.000684 approximately. So now the probability after updating with the information, that is the probability of probability of theta given the data, 1 over the number I just said is 1462.48 times theta to the 5110 times 1 minus theta to the 4110, or this picture. So we had a very flat number. We hardly had any information about it. And we came up with this results. The average is 51 over 92, or about 0.55. And the mode, the place where it's flat up here, is 0.569. Those are 2 measures of centrality, as it's called in a probability distribution. They don't have to be the same, and they aren't in this case, 0.55, 0.569. We have what are called credence regions. The 95% credence region is from about 0.25 to about 0.84. Here, the actual numbers are down a little bit later. I don't remember what they are. But this has considerably shrunk the amount of uncertainty that you have. That is the 95% credence region. So it's still awfully wide. The credence region is 0.2468 to 0.8369. As I mentioned before, I personally know about 90,000 flips. So what would my posterior look like? Well, you can see I cut the region here to only show between about 0.51 to about 0.535. And the distribution is considerably narrower than it was before. I drew a little triangle here that has area 1 just to show that the area between these two is 1, as they have to be as probability distributions. So this is what the data looks like. And the answer, by the way, is about 0.538 for the mean of the posterior on my data using about 90,000 flips. Now, my credence region is 0.520518 to 0.527065. The region of my 90,000 flips credence region to the one we had before is about 90, even though I had about 13,000 times as much data. So this is part of what I was talking about before, where people have almost no understanding of how data will affect the uncertainty associated with it. And so even though I have 13,000 times as much data, I only have a reduction of less than a factor of 100.
That sort of follows a general rule in probability theory that the root mean square divided by the mean goes as 1 over the square root of n. You're not following that exactly there, but if that 90 were 110 or 120, then it would be following that 1 over square root of n rule.
Right. But the square root of n is unfortunately not based on Bayes' rule. It's based on the frequentist formula, and which doesn't take into account the uncertainty that you have and the prior information that you have and all the rest of that.
So one of the other things that's important to take away from this is most every one of you went through a really elementary statistics course in which you were taught about how you can get more and more accurate measures of the mean. But here we're talking about how much data it takes to get an accurate measure of the standard deviation or the spread around the mean. And the idea is it's much, much harder to estimate a standard deviation than it is to estimate a mean. And it's usually the standard deviation you really care about, because that's really what tells you what you can rely on and what the risks are of making the wrong decision.
Absolutely correct. Thank you, Jack. I assume that was you, Jack. I don't know who said that, but yes. Thank you. Yes, thank you. Okay. So you should notice in the case of where a few observations are, the prior distribution plays an important part in the estimation of the uncertainty. The posterior standard deviation that Jack was just talking about will be much more important about the standard deviation of your prior than of your posterior. But if you have a large number of observations, the prior is essentially forgotten. So that's the reason that Steve had said that the credence region was close to what a frequentist would call a confidence region. Okay. So,
Quick question.
yeah.
Based on what you know, if someone gave you 10 tacks, put them in your hand, and said, okay, if you pick the number that show up heads, or point up, point down, one of the outcome states, you get X dollars. What number would you pick?
Well, based on what I mean, assuming that they're similar to the tax that
your tax, these tax.
Right. Then my number would be 0.538 because that's the mean. And you can show that the best choice would be to choose 0.538 times the number of flips.
No, you have one. I'm saying this takes events like this and then brings them down to very short, small samples. You have one time to turn over these 10. You have 10. So you're going to have pick a number between 0 and 10. What number would you pick?
I would choose 0.538 times 10. I would choose 5.38.
Okay. Well, which means you'd say it would be 5 tacks would be up. You'd have an even number of tacks up and an even number of tacks. You'd have 5 up and 5 down.
Yeah.
Okay. So you would say, okay, that's my best guess is 5 up, 5 down. But the probability of you getting 5 up, 5 down are not very high.
What do you mean? I mean,
the highest it's the best guess.
It's the best. No, I'm saying it's the best guess. I'm just curious. I mean, this goes back then to how people make decisions, and that's all. You were talking
right.
about.
But the if you have a square difference as the utility number, then using the mean is always the right answer. That you can show that to be true for any decision, if that's the form of your utility form. If you have a different one, you have to have a different calculation for what it is. But you have to have some kind of a loss function for a decision. And if the loss function is squared, then the mean is the answer. And that's what I was assuming was what you were asking for.
Yeah, I was just curious. Thank you.
Okay, but that, we're talking about game theory here and not probability theory. In game theory, you need to know not only the probabilities, but you need to know the possible choices. You need to know the values of each of the outcomes. I mean, it's a much more complicated structure than just the probabilities. Okay, so this is about as far as I've been able to get in this week. And I'll just go over what we've done. We did a short history of modern probability, Kolmogorov's axioms, the monotonicity, the complement rule, the numeric bounds, the sum rule, God's probabilities versus Bayesian probabilities, frequentist versus observer dependent, events and probabilities of events, random variables and their domains, probability distributions, joint probability distributions, marginal distributions, conditional distributions, the product rule, Bayes rule. Then we did a couple of side steps and did the Monty Hall problem and Bayesian learning. We learned about prior distributions and posterior distributions. By the way, the one that I showed you very narrow, that is my prior for any new ones coming up. So if I had a decision with some particular loss structure, I could do the calculation to figure out what's the best decision for any particular loss structure.
Could you go back 2 screens where it talked about entropy being, yeah, right there.
Yeah,
Wait a minute.
there is, okay, so entropy is based on probability, both in terms of statistical mechanics and Shannon's information entropy. And we're going to talk about those in the future. I couldn't get into them today, but those and the relationship between thermodynamic entropy and Shannon's information entropy is what is our final goal. That's what we want to be able to understand, how the fact that Shannon information entropy is actually identical to thermodynamic entropy, which we've talked about in the past, using heat and energy and work and all of those things that we've talked about. So where the place we're going to is to show that those two are actually identical.
Well, thank you, Bob. I've
Sure.
got to run.
Yep.
Thank you, Bob. Very, very well done.
Yeah, thanks a lot. This was great.
Okay. I'm
Thanks,
glad
Bob.
we were able to deal with it, and I'll continue next week, and in a couple of weeks, in 3 weeks, Jessica will switch to CRISPR and virology and COVID-19 and whatever. Thanks.
Thank you again.
Thank
Hey,
you.
thanks a
Bye.
lot.
Hi,
Thank you.
everyone.
Thank you.
Bye.
Bye.
Bye. Bye, Chris.